So now we are ready, and the second talk of the session is going to be given by Sally Dong, and she's going to talk about a nearly linear time algorithm for linear programs with small previews. Yes.
Okay, thank you, and sorry about the technical difficulty. So today I'll be talking about linear program solver based on IPM that is parameterized by Treewidth, and this is joint work with Exactly and Wang. Okay, so the type of linear programs that we want to solve in our paper is of the following form. So we have the standard C transpose X that we're minimizing, subjected to AX is equal to B, and X is bounded on both sides. And we will just make the assumption that this matrix A is of full rank, and we can assume also that the number of constraints is less than or equal to the number of variables. And here we have the additional constraint that the Treewidth of A, which we'll define in the next slide, is going to be at most some constant tau, or it doesn't have to be a constant. Okay, so what is a Treewidth of a matrix? So first, given this matrix A, which is of dimension d by n, we are going to define the dual graph, which is going to be on d vertices, and the edges are going to be added as follows. So every vertex is going to be a row of A, and we add an edge between vertex I and j if and only if there is some column k such that A is non-zero in that column. So row I is non-zero in that column, and also row j is non-zero in that column. So as a quick example, we have this matrix A, and here we only care about the non-zero pattern of A, and we don't actually care about the values of all the entries. So A here is 8 by 10, so we have 8 vertices, and basically what we do is we go through all the columns, and for every column, so for example, for column 3, we have non-zero entries in row 4, 6, 7, and 8, and actually this leads us to having a cleat on the vertices 4, 6, 7, and 8. Okay, so with this definition, we are going to define the Treewidth of this matrix A to be the Treewidth of this graph. And actually, one immediate thing we can notice is that every column of this matrix A corresponds to a clique of the graph. So if the Treewidth is bounded by tau, then there cannot be cliques of size larger than tau in the graph, which means that the column sparsity of A is also bounded by tau. Okay, so now our main result is as follows. So we're solving a linear program of the form that I had just described, and we're doing this to epsilon accuracy, and the runtime is going to be linear in the number of variables, quadratic in the Treewidth, and also we have this log of the accuracy. So we should mention that this is not a strongly polynomial algorithm because we're using interior point methods. So we're actually running, the expected time is the number of arithmetic operations. And when we say we're solving this to epsilon accuracy, here we can say that if the entries of the matrix and also the constraint vectors are integral, then we can choose epsilon to be 2 to the negative big O of this L, which is some bit complexity of the 2 norm of B and C, and delta here is going to be the maximum of all the subdeterminants of the matrix A.
Wait a minute, can you go back? Let me process. Okay, this is to make it, to have an accurate solution.
Exact solution.
Exact solution. All right.
And we also have a convex generalization of this and it basically generalizes to the x being in some convex set, and we have to restrict all these to be of constant dimension. So we break up x into subvectors of constant dimension, and each subvector is contained in some convex set. Okay, so of course there are a lot of related works in terms of parameterizing by Treewidth, but I'll just mention a couple that is more related to what we do. So already many years ago, there's sparse linear system solvers where they take advantage of the sparsity of the matrix. And so here, this is following a long line of work, actually by George and Liu. And this here itself is a textbook, I believe. And so they give actually some Fortran implementations of their algorithm where they're solving linear systems of the form AX equals to B, where A is symmetric, positive, definite. And even though they don't explicitly say that their algorithm is parameterized by Treewidth, it actually is. So what they do is they just talk about matrix sparsity by itself. Okay, and of course, more recently, we have some authors here at the workshop. There's this paper in SOTA 2017 that shows how to solve linear systems that is fully in fully polynomial time, except they use a different Treewidth definition than we do in our paper. And also they have some results on, for example, max vertex flow and also max matching. And actually in this paper, the authors had already conjectured that you can also solve linear programs that is fully parameterized and fully polynomial time in the Treewidth parameter. And finally, there is work by Fritz and Jana and others at the workshop where they give a strongly polynomial time algorithm for solving linear programs, and that this is also parameterized by Treewidth, well, not Treewidth, Treedepth, which has an upper bound of Treewidth times log m, where m is the number of constraints, and Treedepth is already lower bounded by Treewidth. And since they're solving everything exactly, and also this is strongly polynomial time, you would expect this 2 to the O of d times 2d, something like this in the runtime. So they get nearly linear and, right, so parameterized by Treedepth. And here their delta is a little bit different than our delta, but not so much. Okay, so I'll just briefly mention one application, which is to the min-cost flow problem, which we can write in the following form, where A is going to be the incidence matrix of the input graph G. And if you actually remember how we defined our graph in order to define the Treewidth of the matrix A, the graph actually has the same adjacency pattern as the matrix A transpose. And here A transpose is the Laplacian. And in fact, we have that the Treewidth of A is equal to the Treewidth of the input graph. So this works out perfectly. And for other flow problems, the Treewidth of the matrix is generally on the same order as the Treewidth of the actual graph of the input, of the graph in the input. Okay, so since this is an IPM algorithm, we can just begin with a brief overview of what IPM gives us. So just as a super quick overview, I think a lot of you have already seen some of this from another talk of mine. So the interior point method, basically what we're doing is we're walking inside the polytope slowly until we get to the optimal vertex. So we write our linear program in terms of both its primal and dual solution. So we have the primal space P and dual solution space S, and we're following some central path given by this following equation here, and basically we're just adding a barrier function so that our x will eventually always stay within the feasible set. And if we take t to go to 0, then this x of t approaches the optimal solution. Okay, so in terms of actually writing this out in pseudocode, this is what happens. So here we have this projection matrix, which we define to be what's written there. And basically, you will iterate until your t is small enough, until you get to the accuracy that you want. And at every iteration, you update this diagonal weight matrix D, and you update the direction which you want to take the step. And then you basically take a step in S and X, and then also take a step in X. And at the end of the iteration, you decrease t and you repeat. And in our paper, we use instead a robust interior point method. And here, basically, what we do is rather than maintaining, so the difficulty in implementing interior point method quickly is that this update calculation can take a long time. Okay, so what we do is instead we maintain some approximations to our solution. So this is going to be our x bar and s bar. And now we will compute everything that we need in terms of these approximations rather than the actual central path parameters. And then we will make some implicit update to our actual central path solutions. And we will, again, decrease t by some factor, and then we update the approximations in case the approximations are no longer good enough with these updated x and s. And the guarantees that we have is that the total number of iterations we need to do this is about square root n times log 1 over epsilon. And also, when we say we're maintaining x bar close to x, we mean in this sense. And central path also guarantees that when we are updating x bar to be close to x, in total, the number of coordinates that we need to change is going to be approximately linear throughout the entire algorithm. And this will come into handy, it will become very handy later because if x bar changes only in a linear number of coordinates throughout the algorithm, then since this weight matrix D is a function of x bar, this will also only change in a nearly linear number of coordinates throughout the algorithm. And this will allow us to bound how much time we need to compute in these two expressions. All right, so now on to the part where we actually use the Treewidth. So remember, in this projection matrix, we have this term ADA transpose. And this thing inverse is kind of a headache to compute. So here we note that ADA transpose is a positive definite matrix. And actually, I should mention it has the exact same non-zero pattern as AA transpose. And since it's positive definite, we can uniquely factorize it as L transpose, where L is a lower triangular matrix. So in general, this factorization is not very helpful because L can be dense. Except we note that reordering the rows of A doesn't change the meaning of the LP because you're just reordering the constraints. It doesn't change the graph either, but it does change the resulting factor, L. So this is what we do. We will reorder the rows of A. And just for those of you who don't know, Cholesky factorization is actually just doing symmetric Gaussian elimination in a matrix. So here, for example, I have this matrix A transpose, which is symmetric positive definite. And say I want to eliminate the first row and column, which means that I want to zero out these entries circled in red. Then what I do is basically, as you remember in Gaussian elimination, I'm going to take the 10th row and then subtract some multiple of the first row and replace the 10th row by this, right? And this is equivalent to multiplying on the left by a lower triangular matrix. And then to eliminate the top right corner entry, do the same thing, but you're multiplying by upper triangular matrix on the right. And basically, we're just going to eliminate the rows and columns from 1 to 10. And so this gives us a sequence of row-column operations, and each of them together, you multiply them, and you get this factor out. Okay, so like I've said already, we want to reorder the rows of A so that when we do this factorization, we end up with less non-zero entries. And so reordering the rows, this is called finding an elimination order. And it has also a corresponding elimination tree, which I'll explain. So again, an example, when you do the Cholesky factorization, you can get from M to this factor L. And so it has some very interesting properties in terms of its non-zero entries. And like I said, so there's an elimination tree, and how is this built? Basically, we have one vertex for every row/column of A, of L. And so, for example, I have this vertex 1, and a vertex, its parent is going to be the node corresponding to the entry right below this 1, 1 entry in the matrix. So here, this is non-zero only in entry 10, so its parent is going to be 10. Okay, so for example, vertex 6 has directly a non-zero entry so in column 6, there is also a non-zero entry already in row 7, so the parent of vertex 6 is vertex 7. So you get 6 to 7. And so overall, the property you get is actually that the non-zero entries in every column of L is going to be a subset. So in column J of L, it's going to be a subset from the path, on the path from the vertex J to the root in this elimination tree. So if we have some data structure based on the elimination tree, it can basically help us to keep track of the non-zero entries of L. And then we'll be working along this elimination tree when we need to update L. Okay, so there are some interesting graph parameters here. I'll just state this theorem that's already quite old, so nothing I've presented is new so far. So the theorem says when you have a graph on n vertices, then this relation is true. So what is the separator number? This you can just think of in general as the size of the balanced separator in your graph, whose the minimum balanced separator in your graph, whose removal gives you two subgraphs of balanced size, right? And so here, tree depth is actually exactly the same as the minimum elimination tree height. So that in the definition of tree depth already, this is how it's defined. And for example, in order to relate tree width to the separator, we know that if you have a tree decomposition, then you can take a bag. You can find a bag in the tree decomposition that separates your graph into balanced subgraphs. So since the bag sizes are bounded by the tree width, then you get that the tree width is an upper bound on the separator number, -1. Okay, so with this big relationship, we have the following. So there's a very recent theorem in Fox 2021 who shows how to compute a tree decomposition of this width, which is going to be some polywog approximation of polywog n approximation of the actual tree width, and this is going to be in nearly linear to m time. So in our case, we have m is going to be n times t, or more specifically d times t, and using this theorem, we can get that we can find this elimination order so that the elimination tree has height tree width of a times some log factor in this very nice running time as well. Okay, and suppose we have this elimination order and also this elimination tree, then we have the following nice properties about how to factorize the matrix A transpose into the Cholesky factors. So we can do this in a very good running time. The factor ends up having good column sparsity, and you can solve for L inverse given a specific vector V in some time that is proportional to the non-zero entries of V. And also it's easy to update L in terms when D changes. So when a coordinate of D changes, actually what's happening is that you're rescaling the columns and rows of, you're rescaling the columns and rows of, sorry, you're rescaling the column of A and the row of A transpose.
Can I ask here? I mean, there you don't have numbers anymore. I mean, the length of the bit length numbers. But don't you leave the rationals when you do that? I mean, I'm a bit confused.
Yes. So we're only counting, I guess, the number of operations and
in the raw model or in the real model, or
yeah, I guess so.
Okay.
Yeah. Okay, right. So basically, what happens is when A's entries in row I is updated, which means that M's entries in row and column I are updated. So for example, if we were to update these guys, then what we need to change in L is actually just going to be column 6, and from 6 up to the root in the elimination tree, so we'll need to change column 6, 7, 9, and 10. And it turns out that you don't need to change column 8. And this allows you to bound the number of operations you need to do when you update L. Okay, so, sorry, what time do we start?
5 minutes.
Okay. Okay, well, but I think that was maybe the most important part in terms of making use of the Treewidth. So just recall very quickly, so at every step of the IPM, we're updating the current solution of X using this formula. So here we have this ADA transpose inverse, which we replace by the Cholesky factorization. And just for convenience, we'll ignore this middle term, because if we can deal with the last term, then the middle term is going to be easy. Okay, so then what we're going to do is we split this big expression up into 2 parts, one of which we call this multi-scale basis, and the second part we call the multi-scale coefficients. So at every iteration, actually, we can always compute the H exactly, but anything, so if you want to work with this multi-scale basis, you cannot actually make this computation because this L inverse transpose is a very costly thing to work with. And you should just think of this as kind of some linear combination of the columns of this W transpose. So like taking a combination of your basis vectors. And in the algorithm, we'll maintain x implicitly using the following property. So what we'll actually maintain is this x hat, we'll maintain d, we'll maintain this vector h, which is corresponding to the h up top, and, sorry, some h, not exactly the h up top, and this epsilon is going to be some leftovers. And this w, we're not actually computing, but we have implicitly the matrices L, not the inverse transpose, and also A and D. And we have some properties in terms of being able to update this representation in a good time with every IPM update. So for example, we can compute individual coordinates of x in time of tau squared. And you do this by taking the transpose of what you need to compute, and then this ends up working out. And to take a step in x, which means, adding this to what you currently have, actually we just need to increment c. Oh, sorry, so c is also some real number that we're maintaining in the algorithm. Okay, and when v updates, then we need to change the representation somehow by changing h and e epsilon. And the most complicated thing is that when d is updated, then this Cholesky factor needs to change. And so we update this Cholesky factor, we push the changes to this vector epsilon, and also we need to update h epsilon and x hat, because d changes in two places, one here, one at the beginning, and then once here in the factorization. Okay, but because we have this nice sparsity guarantees in our matrix, everything works out. And finally, in the robust IPM, we need this data structure to detect when x bar differs from x by a lot. And to do this, we have the following informal theorem statement, which is that if you have a sequence of vectors that are slowly changing, and the sequence is of length k, and you know that you can access individual coordinates of one of these vectors, and also you can estimate the L2 norms of certain subvectors of xi for every I, then you can maintain a sequence of approximations so that at every term in your sequence, you have actually the approximation that you want. So what is this JL sketching, and what exactly is it for this part? Okay, so we need to define the sampling tree, which helps you to sample a coordinate of your vector x. So basically what happens is, in this tree, this is going to be a constant degree tree of height h, and we have n leaves labeled with 1 to n. So they're going to correspond to the entries of this vector x. And at every non-leaf node, you label it with all the labels of the leaves in your subtree. So basically, you start off with something corresponding to the entire vector, and you're just going to partition the current subvector at every node into the leaves. Right? So this is going to be the whole vector x, and this is going to be x1 through 4. Here is x5 through 9, and so on. And we're going to keep this Johnson-Lindenstrauss sketching matrix phi, and at every node we're going to maintain a phi restricted to the coordinates that you're interested in times x. So really what this accomplishes is that at every node, so at the top node, we have an approximation to the two norms squared of the entire vector, and at every node that is not a leaf, we have an approximation to the two norms squared of the subvector that we're looking at the point at this node. And then at every leaf node, we just have the entry squared. And with the sampling tree, obviously, it's very easy. So in order to sample a coordinate of x with probability proportional to xi squared, because you just take a random descent down the tree starting from the top. So you generate a random number, and if it's less than, from here, you get a random number. And if p is less than the proportion of this guy over the whole thing, then you go down this way, and if not, you go down the other way. Okay, so we're going to use the sampling tree in order to maintain some sketch of the vector x. And remember, x is represented in this complicated form, and let's just consider this most involved term, which is of the following form, and then we need to also update our sampling tree every time L and D and H changes. By the way, we think that maybe this can all be simplified if we don't care about the exponent of the Treewidth parameter in our runtime. So if we want just Treewidth to some constant, then this might actually all not be needed. Okay, and so one last thing is, how do we define the sampling tree? And remember, because we need to update D, L, and H at every node of the sampling tree, when they update, we need to be able to actually not do all these work that possibly might be unnecessary in case it doesn't actually change. So we need to define the sampling tree in a clever way so that the updates we do are restricted to only paths from the root to, from some leaf to the root, or in some subtrees. So I'm out of time, but basically we define the sampling tree based on the elimination tree. Okay, and then when H changes, actually you can show that you only need to update the sketches along the path from the coordinate that you've changed to the root. And when L changes in some column I, the updates are also just restricted to a path from the coordinate to the root, and also a subtree. So updating a path is easy because this is in O of tau time, and updating a subtree is actually difficult, so we don't do this until we actually need it. And then you do some clever data structures to make it all work out. And finally, I'll just conclude with an open question, which is that I really am interested in whether or not it's possible to incorporate some of these ideas to the strong polynomial time LP solver by Fritz et al. And with that, I'm done.
Okay, thank you.